All right, so now that we know what the formula is to determine the distribution of shear stress, so the transverse shear stress which acts upon a section, let's go back to sort of one of the first questions that we got asked when we looked at shear stress all the way back to average stress, and that is, well, how does this, what does the profile of that shear stress look like? And so what we're going to do is we're going to look at a rectangular section, so something that's really straightforward and commonplace, and we'll just kind of see, well, what does that distribution look like? So remember again that the shear stress at the surface is going to be VQ over IB, and that just equals V times A1 times Y1 over IB. That's just because Q is A1 times Y1. So what do we have here for these numbers? So the shaded area is A1. And so I've got the neutral axis, and really that's our coordinate system. So the neutral axis is going to be y equal to 0. And so the place where we're looking for the shear stress is right here. It's right where this red line is. So A1 is the area above this red line, and that's the distance y that we're looking at. Now, what will get just slightly confusing is that this y1 is the distance from our base point at the neutral axis to the centroid of this area, A1. So that's y1. And so with that, now we kind of have everything that we need. And it's really just going to be working through the equation, and then we know what our profile looks like. So let's do that. The first thing we need to do is find the constant I. So let me just put our width B in there. So for a rectangular section, I equals 1 over 12 B D cubed. All right, that one's pretty straightforward. I'm sure many of you have that sort of etched into your memory. And then, yeah, let's look. So our shear stress, if we plug that in, we get V times A1 times Y1 over 1 over 12 B D cubed. That's I times B. And now it's really a matter of expanding this out. So let's bring the 12 up here. 12V. And so the first thing we need to do is look and see, well, what is this A? Well, we know it has width B, and it's going to have the height D over 2 minus Y. So that's our area. D over 2 minus Y times Y1 over B D cubed times B. These two B's cancel out. So we end up with 12 times V times D over 2 minus Y. Now Y1, well, that's just our centroid location. And so essentially that's just going to be the average distance between the height from the extreme fiber to the neutral axis and our distance y here. So that's how we'll write it out. That's a nice convenient way to look at it. So it'll be D over 2 plus y divided by 2. And like I said, that's just the average distance between these two. That's where our centroid is. and that's going to be all over d cubed times b. All right, so we'll move, that 2 comes down there, that cancels that out. We'll do just a little bit of rearranging. So that will give us 6v times, then if we times d over 2 minus y times d over 2 plus y over d cubed times b. Let's multiply this out. So we end up with 6 times v, first inside, outside, last. We're going to end up with d squared over 4 minus dy over 2 plus dy over 2 minus y squared all over d cubed times b. These 2 cancel out, and so we're just going to end up with 6 times v over d squared over 4 minus y squared d cubed times b. Multiply that by 4. And we then end up with 6v d squared minus 4 y squared over 4 d cubed b. 4 moves down, that divides out, and we end up with 3 d squared minus 4 y squared over 2 times b d cubed all times v, tau of y. So, yeah, that seems like a big algebraic exercise there, but it does show us something important, and that's that our shear stress in the y, for a distance y here, our shear stress varies parabolically. It varies by the factor of y squared. And so for a rectangular section, tau y varies parabolically with depth. And that's kind of powerful and really important, because this is true for any rectangular section as long as it's loaded parallel to its strong axis. So you'll get shear stress distribution in the web of an I section also varies parabolically. We will see here in a moment that the flanges on there mean that it's not a huge change over that depth, but it is a parabolic behavior. You'll see this in the webs of C channels as well. Just for a final point, just to have a look at to sort of prove our previous assumption that or the shear stress is the maximum at the neutral axis. So for the neutral axis, that's really going to be when y equals 0. And so if we look at tau y equals, if we plug y equals 0 into here, we get 3 times d squared over 2 times b d to the cubed. That squared cancels out, and times v. That cube cancels out, so we get tau max equals 3 over 2 v over b d. Well, this is kind of interesting, because this is what we first looked at with average shear stress. B over d is just the area. So this is saying that the maximum shear stress for a rectangular section is going to be 3/2, so 50% larger than just the average shear stress. So that's the same. Tau max equals 3 over 2 v over a. Just the same thing there. And so if we look at that as a stress distribution, so our actual stress distribution, if this is our neutral axis, again, it's going to vary parabolically, and that's going to be tau max equals 3 over 2 v over a. If we were to assume only an average shear stress, tau equals v over a, so that's tau average. You can see, yeah, we really underestimating what that shear stress is. So I hope that was enlightening. It's, one, just to sort of show you what that distribution is, but then also to just kind of give you a little bit of practice with using the finding shear stress at a particular depth. So with that, we'll wrap that one up here.